Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Before we dive in, let's do a quick recall from episode 2. Try to remember, what was the typical RTO for a hot-warm pattern? Take a second. It was 5 minutes. 5 minutes from detection to recovery, 1 minute for Aurora promotion, 4 minutes for everything else. And what about RPO? Recovery point objective. How much data loss you can tolerate? Remember the e-commerce example? Aurora had 1 second replication lag under normal load. But during the actual failure, replication lag had climbed to 45 seconds. That became the RPO, 45 seconds of lost transactions. Those numbers aren't magic. They come from how Aurora actually works under the hood, the 6-way storage replication that nobody explains, the quorum-based writes that make sub-second lag possible, and the edge cases where everything breaks down. Today, you're going to understand exactly what's happening during that replication. More importantly, you'll know where Aurora Global Database breaks and how to design around it. By the end of this lesson, you'll be able to explain how Aurora's 6-way replication works, the quorum model, the storage layer separation, and why this matters for multi-region. You'll calculate expected replication lag and determine if your application can tolerate it. We're talking 45 to 85 milliseconds under normal load, 1 to 30 seconds under stress. You'll know when to use Aurora Global Database versus native Postgres replication. They're not interchangeable. And you'll handle split-brain scenarios, what happens when regions diverge and how to prevent data loss. Let's start with why Aurora exists in the first place. Traditional RDS Postgres has a fundamental problem with multi-region. Your primary database writes to local storage. Every transaction hits disk. To replicate to another region, Postgres ships the write-ahead log, the WAL, across the network. Then the replica applies those changes. Problem 1. You're sending entire log records across regions. High bandwidth, high latency. Problem 2. The replica has to replay those writes. CPU intensive. Falls behind under load. Problem 3. Failover takes minutes. The replica needs to finish applying all pending WAL records before it can accept writes. I've watched this happen in production. Primary region fails during peak traffic. Replica is 30 seconds behind. You promote it. But first, it has to catch up. Apply those 30 seconds of pending changes. Your RTO just went from immediate to 3 minutes. Aurora rethought the entire architecture. Here's the key insight. Separate compute from storage. Your database engine, the compute layer, doesn't write to local disks. It writes to a distributed storage layer. That storage layer handles all replication automatically across 6 storage nodes in 3 availability zones. The database engine just sends redo log records to storage, not full data pages, just the minimal change log. Storage applies those changes and replicates them. This separation is what makes multi-region possible. With Aurora Global Database, you're not replicating database to database, you're replicating storage to storage. Physical block-level replication, not logical transaction replay. Primary region writes to its 6-node storage cluster. Those redo logs ship to the secondary region's storage cluster. Storage applies them. Secondary region's database engine reads from its local storage. Result? Sub-second replication lag. Fast failover, no CPU overhead on the secondary. Now let's talk about what's actually happening with that 6-way replication, because this is where the magic happens. Each Aurora database writes to 6 storage nodes, not servers, storage nodes. These are distributed across 3 availability zones in a region, 2 nodes in AZA, 2 nodes in AZB, 2 nodes in AZC. When your application commits a transaction, Aurora writes to storage. But here's what most engineers don't realize. It doesn't wait for all 6 nodes. It uses a quorum. 4 out of 6 storage nodes must acknowledge the write. That's it. 4 acknowledgements, and the transaction is considered committed. Why 4? Let's think through the math. If you lose an entire availability zone, 2 nodes, you still have 4 nodes up. Your database keeps writing, no interruption. That's the availability part. But why not 3? Why not make writes succeed with just 3 acknowledgements? Because you also need to handle reads during partial failures. Aurora requires 3 nodes to acknowledge reads. If writes required only 3 and you lost 2 nodes, you might read stale data that doesn't include recent writes. 4 for writes, 3 for reads. This is called quorum consistency. Here's the critical part. Write quorum plus read quorum must be greater than total nodes. In Aurora, 4 plus 3 equals 7, which is greater than 6. That guarantees consistency. Any successful read will see all previously committed writes. Let's walk through what actually happens during a transaction. Your application executes backquote, insert into orders, values, backquote, and commits. Step 1. Aurora's database engine generates a redo log record. This is minimal, just the change, not the entire data page, maybe a few kilobytes. Step 2. Database engine sends this redo log record to all 6 storage nodes in parallel, not sequentially, all at once. Step 3. Storage nodes write the record to persistent storage. They're using SSDs, so this is fast, single-digit milliseconds. Step 4. 4 nodes acknowledge the write. As soon as Aurora receives 4 acknowledgements, the transaction is considered committed. Your application gets success. The other 2 nodes? Aurora doesn't wait for them. Step 5. Those 2 slower nodes eventually catch up. Aurora doesn't block on them. They're part of the durability layer, but not the latency path. This is physical replication. Aurora ships redo logs, byte-level changes to data blocks, not SQL statements, not logical transaction records. Compare to Postgres native replication, which is logical. Primary ships SQL-level changes. Replica parses them, executes them, updates its tables. Every write costs CPU on the replica. Aurora's physical replication, storage applies block-level changes directly, much faster, much less CPU overhead. Trade-off. Physical replication requires identical storage format. You can't replicate Aurora to non-Aurora databases. Logical replication is more flexible but slower. For Aurora Global Database, the primary region's storage cluster ships redo logs to the secondary region's storage cluster. This happens asynchronously. It doesn't block commits in the primary. Secondary region's storage receives redo logs, applies them to its 6-node cluster using the same quorum model, 4 of 6 writes. Secondary region's database engine reads from this replicated storage. Typical lag? 45 to 85 milliseconds. Let's break that down. US East 1 to US West 2 network latency, about 15 milliseconds. Storage apply time, 30 to 70 milliseconds depending on write volume. For most applications, 85 milliseconds is invisible. User creates an order in the primary region. Secondary region sees it a tenth of a second later. No one notices. But under heavy write load, replication lag can spike. Here's why this happens. High transaction volume means the secondary storage cluster is applying redo logs as fast as it can. If writes come in faster than storage can apply them, a backlog builds. I've seen replication lag hit 10 to 30 seconds during Black Friday level traffic. The secondary is always catching up, never caught up. The redo log queue keeps growing. What this means: If the primary region fails during this lag, you lose the uncommitted data in transit. That's your RPO, the replication lag at the moment of failure. Remember episode 2? The e-commerce company with 45 seconds of replication lag during their outage? This is why it happened. They were under heavy write load when the primary failed. Here's a common failure pattern that trips up even experienced engineers. User updates their profile in the primary region. Application redirects them to a page that reads from the secondary region for load balancing. If replication lag is 200 milliseconds, the user sees their old profile. They think the update failed. They update again. Race conditions, data consistency bugs, support tickets. Solution: sticky sessions. After a write, route that user's reads to the primary region for the next few seconds. Let replication catch up. Then you can send reads to the secondary. This is called the read your own writes pattern. It's not automatic, you have to design for it. Now let's talk about when Aurora Global Database breaks down, because it's not a silver bullet. Scenario 1, high write throughput. Aurora Global Database can handle about 200,000 writes per second in the primary region. But cross-region replication bandwidth is limited. If you're pushing 100,000 plus writes per second, replication lag will consistently be multiple seconds. At that scale, consider sharding across multiple Aurora clusters, or switch to DynamoDB global tables, which we'll cover in episode 6. Scenario 2, large transactions. Aurora limits transaction size. If a single transaction modifies hundreds of megabytes of data, replication lag spikes. The secondary storage cluster takes time to apply that massive redo log batch. Solution: break large transactions into smaller ones, or accept longer lag for batch operations. But understand the trade-off. Scenario 3, split brain during failover. What if there's a network partition between regions during failover? Primary region thinks it's still primary, keeps accepting writes. You've promoted secondary to primary. It accepts writes. Now you have two primaries, both accepting writes. Different data in each region. Aurora prevents this with safeguards. When you promote secondary, it force demotes the primary. But if the network is completely partitioned and you force a manual failover, you can create split brain. Prevention: always use Aurora's managed failover. Don't manually promote unless you're absolutely certain the primary is dead. And even then, be careful. And let's talk about cost reality. Aurora Global Database isn't cheap. Primary region, standard Aurora costs. Secondary region, storage replication costs, plus read replica costs. For a 1 terabyte database with moderate write load, you're looking at approximately $800 per month primary, $600 per month secondary. Plus cross-region data transfer, 2 cents per gigabyte. Writing 10 gigabytes per day across regions? That's an extra $6 per month data transfer. Not huge. But at 100 gigabytes per day, you're at $60 per month just for data transfer. This adds up fast at scale. Now let's talk about common mistakes, because I've seen these repeatedly. Mistake 1. Assuming zero lag. You architect for immediate consistency, assuming Aurora replication is instant. It's not. Typical lag is 50 to 100 milliseconds. Under load, multiple seconds. Fix: design for eventual consistency. Use read your own writes patterns. Show users your changes are being replicated messages if necessary. Mistake 2. Not testing failover under load. You test failover with zero traffic. Works perfectly. 90 seconds, just like AWS promised. Then production fails during peak load with 10 seconds of replication lag. You lose those 10 seconds of transactions. Fix: test failover under realistic load. Measure actual RPO. Communicate this to business stakeholders. Don't promise zero data loss if you can't deliver it. Mistake 3. Confusing Aurora Global Database with multi-master. Aurora Global Database is not active-active. It's active-passive. Only the primary region accepts writes. Secondary is read-only until promoted. If you try to write to the secondary, it errors. Your application needs to know which region is primary and route rights there. Fix. Use a route 53. CNAME for your write endpoint. Update it during failover. Applications always connect to the current primary. No hard-coded region names in your code. Before we wrap up, let's test your understanding. Pause and answer these questions. Question 1. Why does Aurora use 4 of 6 quorum for writes instead of 3 of 6? Question 2. What's typical replication lag for Aurora Global Database under normal load, under heavy load? Question 3. You have a photo sharing app. Users upload a photo, then immediately see their gallery. Can you safely read the gallery from the secondary region right after upload? Why or why not? Take a moment to think through these answers. Question 1. 4 of 6 ensures that even if you lose an entire availability zone, 2 nodes, you still have 4 nodes for writes. And with 3 of 6 read quorum, write quorum plus read quorum equals 7, which is greater than total nodes. This ensures consistency. Question 2. Normal load, 45 to 85 milliseconds. Heavy write load, 1 to 30 seconds. This is network latency plus storage apply time. Question 3. No, not safely. With 45 to 85 millisecond lag, the photo might not be replicated yet. A user sees the old gallery without their new photo. Solution. Read from the primary region for that user's session after they upload. Or implement sticky sessions that keep writes and subsequent reads in the same region. Let's recap what we covered. First, Aurora separates compute from storage. The database engine sends redo logs to a 6-node distributed storage. Storage handles replication using a 4 of 6 write quorum. This separation is what makes sub-second replication possible. Second, physical replication beats logical for multi-region. Aurora ships block-level changes, not SQL transactions. Faster, lower CPU overhead. But it locks you into the Aurora format. You can't replicate to non-Aurora databases. Third, replication lag is 45 to 85 milliseconds normally, 1 to 30 seconds under load. Designed for eventual consistency. Use read your own writes patterns. Test failover under realistic load to measure your actual RPO. Fourth, Aurora Global Database is active-passive, not active-active. Only the primary accepts writes. The secondary is read-only. Failover promotes the secondary to primary and demotes the old primary. Your application needs to route writes correctly. Fifth, it breaks down at extreme scale or with large transactions. Above 100,000 writes per second, consider sharding or DynamoDB. Huge transactions cause lag spikes. Break them up. Remember the hot worm pattern from episode 2? Aurora Global Database is how you implement the data layer for hot worm. The primary region handles writes, the secondary is ready to promote in 90 seconds. The 5-minute RTO we calculated, 1 minute was Aurora promotion. The rest was DNS failover and application scaling. Now you know what's happening during that Aurora promotion, quorum shift, storage cluster coordination, write endpoint switch. Episode 2 showed you hot worm patterns. Episode 3 gave you the Aurora foundation. Next up, the compute layer. Episode 4 covers Kubernetes multi-cluster architecture, EKS patterns, control plane considerations, cross-cluster networking. You'll learn how the EKS control plane actually works and why it depends on multiple availability zones. Multi-cluster patterns, independent clusters versus federated clusters, cross-cluster service discovery, and why Kubernetes federation mostly failed, and the service mesh approach that actually works in production. Aurora gave you multi-region data, Kubernetes gives you multi-region compute. You need both to build real, hot worm architectures. See you in the next lesson.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.